All right, greetings, scholars. Beautiful mind here. Let's see. So we are continuing our exploration of Chapter 5, Polynomial and Rational Functions. And here we're going to be working on Section 5.2, Power Functions and Polynomial Functions. Okay. I'm going to go ahead and give a synopsis of what this should be. Let me see. Power functions. Usually those are like monomials. Mono meaning one. Nomial meaning like term. So like one term, like expressions and equations. This is usually like some real coefficient times a variable to a non-negative integer power. All right, so these are things like x squared, 3x to the 4. Usually that's what the power functions look like. And then polynomial functions, a polynomial function is just going to be a finite sum of power functions. All right. Yeah, I think that's a decent way to summarize it. Let's take a look at it. A few learning objectives here. In this section, you will identify power functions, identify end behavior of power functions, identify polynomial functions, identify the degree and leading coefficient of polynomial functions. A power function is a function that can be represented in the form f of x equals kx to the power of p, where k and p are real numbers, and k is also known as the coefficient. Okay. All right, so they'll let p be a real number. That's fine. Oh, shoot. I didn't prepare this properly. Is f of x equal to 2 to the power of x a power function? No, right? Because that's an exponential function. Because exponential, the thing that describes an exponential function is where, wait a minute, yeah, is where the variable is in the exponent, right? So no, a power function contains a variable raised to a fixed power. This function has a constant base raised to a variable power. This is called an exponential function, not a power function. I wonder if I can make that change now. That's okay. So identifying power functions, which of the following functions are power functions? Okay, let's see if we can get this. We will highlight it. Let me see. Let's go like this. Style stroke is thin. Fill like that. Okay. All right, let's see. So a power function is going to be a variable. You have a real coefficient raised to a real power based on the way they described it a moment ago. No. Well, okay. So now I'm starting to like revamp what I said earlier about polynomial functions. The way I used to describe polynomial functions is I describe polynomial functions as a finite sum of monomials. And then a monomial usually takes on the form where you have some real coefficient similar to the power function times a variable raised to a non-negative integer power, right? So once you identify what a monomial is, where you have one term, then a polynomial is going to be a finite sum of monomials. Versus a power function, the difference, I guess you could say that the difference between a power function and a monomial, the power function can be raised to a real number, where the monomial can be raised to a non-negative integer power. The constant function it should not be a power function. Let me see. I would say paste. I would say the identity function is one. Should I extend it across? I mean, I guess we could. Paste. Quadratic function, I will go with that. I really didn't want those to overlap. What I can do is just extend this. I would say the cubic function. Now, on our definition for power function, we said x to raise to a real power. Oh, wait a minute. So then that would include the constant function, because the constant function you can write as x to the power of 0, right? No, wait. Well, if it's, yeah. And then any constant you can write as that number times x to the power of 0, right? So that should be a power function as well. Reciprocal you can write as x to the power of -1, right? So that's still raised to a real power. Reciprocal squared, that's x to the -2, square root. Are all of these power functions? I'm getting that they all are. Uh-oh. I mean, I'm getting that all of them are. So, I mean, that could be the case. I mean, based on the definition that we had on the previous slide, you can get all of these to fit that definition. So I would say that they all are. Okay, let's see how do we do. All of the list of functions are power functions. Wata! Yata, right? In Japanese. I did it, yeah. Right, because they can all be expressed as some real number times a variable raised to a real power, right? Constant function can be whatever that number is times x to the power of 0. Identity function is x to the power of 1. Quadratic function, x to the power of 2. So notice that all these powers are real numbers. You can write all of these raised to a real power, right? Reciprocal function 1 over x is x to the -1. That's a real number. Reciprocal square function will be x to the -2. -2 is a real number. Square root is x to the 1/2. And cube root is x to the 1/3, right? And I think they're basically reiterating what we just mentioned. So, okay, that was interesting. Okay. So these kind of describe like the general shape of power functions. Like whenever you have an even power function like x squared, x to the 4, x to the 6, x to the 17, 18 or whatever, they generally go in this, the tail end of the graph generally go in the same direction, right? So when your leading coefficient is positive raised to an even power, even positive power, right? Then you have they're going to behave kind of like this shape here. If you said, that's not right. Let me think. The k must be the coefficient. So then if you multiply your even power function by a negative, like a negative on the outside, then it's like your y's go from positive to negative. So then they're gonna go down like this. And then the odd power function, whenever you have like a positive leading coefficient times an odd power function, these are things like, x cubed, x to the 5th, x to the 7th, x to some odd power. It usually goes up to the right and down to the left. And then when you say a negative times, it goes down to the right and up to the left. Okay, times an odd power or whatever. Okay. So describe the end behavior of this graph, right? So this is an even power function. We have a positive leading coefficient, so it should go up to the right and up to the left. So we should have something that behaves like this. Okay, so the coefficient is 1, which is positive, and the exponent is 8, which is an even number. As x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to infinity. Okay, so we get something like this. Describe the end behavior of this graph. So now we have a negative. Now, okay, I'm going to go ahead and go a little bit deeper. This is actually leading into this concept called the leading term test, right? And we essentially still have these like 4 characteristics going on. With the leading term test for polynomials, let's see. So like the first case we have is when the degree of the polynomial is even times a positive leading coefficient. So the coefficient tells you about the right-hand side of the graph, and the power or the degree of the degree of the polynomial tells you about the left, right? So the coefficient tells you about the right, If the leading coefficient is positive, it goes up to the right. If the leading coefficient is negative, it goes down to the right. All right, so that's the first thing. The leading coefficient tells you about the right-hand side. A negative leading coefficient tells you about the right-hand side, okay? So then the degree or the power tells you about the left. When the degree or the power is even, right? When the degree or the power is even, the other side does the exact same. So whenever I see even, I know the other side does the exact same thing. So if we go up to the right, then we're also going to go up to the left. Again, even means exact same. So if we're going down to the right, we're going to go down to the left. Okay? And then the way for an odd power or an odd degree polynomial, odd to me means, if even means exact same, then odd might mean what? The opposite, right? So again, the right-hand side comes from our leading coefficient. If it's an odd power or an odd degree polynomial, the other side is going to do the opposite. If we're going down and it's odd, then the other side is going to do the opposite. Okay? So the coefficient being positive tells us we're going up to the right. Negative leading coefficient is down to the right. When the degree is even, the other side does the exact same. When the degree is odd, the other side does the opposite. Does the opposite. All right? So that's the recurring thing. That's how I kind of memorize those. Like, I feel like individually the concepts are simple. The challenge with this course oftentimes is not really grasping the concept. Oftentimes students kind of run into this thing of information overload. It's just like, it's almost like a lot of like quote unquote useless information. It just depends on like what you intend to do with it. But I know that students tend to like underestimate it and like don't take it serious, and then by the time they start taking it serious, it's like now there's all this information that they're trying to process, right? So the name of the game or the trick when it comes to stuff like this, give yourself time. Start as early as possible, and try to get out ahead. So that way when you go to sit down and like review for an exam or something like that, you're not as stressed, versus if you procrastinate with this and this isn't something that you can really do at the last minute and get. It's something that you have to kind of start early and let it marinate over time. And then that's where it kind of sinks in, versus like if you're trying to do it at the last second, you're not going to be able to recall any of the information. So here, notice that our leading coefficient is negative. So our graph should go down to the right, and this is what an odd power, or the power is odd. So that means the other side does the opposite. So it should go up to the left, right? So this graph, now this doesn't really tell us anything about the middle, but we know that as x goes to positive infinity, y goes to negative infinity. As x goes to negative infinity, y goes to positive infinity. So that's what should happen here. And you see that here. Notice it went down to the right and up to the left. Okay, let's see what else we got. All right, wait a minute. Example 3. Oh, okay, so they're just confirming it with the table. Like if they choose several values of x, find the corresponding y. Notice as x goes to positive infinity, y gets closer and closer to negative infinity. As x goes to negative infinity, y goes to positive infinity. Okay, that's fine. So let n be we have polynomial functions. Let's see how the text officially describes this. So let n be a non-negative integer. A polynomial function is a function that can be written of this form. This is called the general form of a polynomial function. Each ai is a coefficient and can be any real number, but the leading coefficient an cannot be 0. Each expression ai x to the I is a term of a polynomial function, right? So again, the way that I like to remember or identify a polynomial function is a finite sum, finite meaning the opposite of infinite. So a polynomial function is a finite sum of monomials, right? And a monomial is a one-term expression where it has a real coefficient times a variable x raised to some non-negative integer power. Okay, so, okay, so let's keep going. So which of the following are polynomial functions? Okay. Now with this first one, if we were to kind of expand that, that would be what, 6x to the 4 plus 4? I would say yes for the first one. It's kind of written weird, but that's okay. Let me see. I would say the first one is, because again, the whole point is can we express it as a finite sum of monomials, right? So if we said the 2x cubed times the 3x, we would get our desired result. I would say yes for f, yes for g, but no for h. Because h, you have that power of a half. Polynomials aren't raised to the power of fractions, or aren't raised to the power of fractions, all right? Polynomials have to be raised to the power of non-negative integer exponents, all right? So these are like our non-negative counting numbers, or whole numbers. So it's like numbers like 0, 1, 2, 3, 4, 5, stuff like that. It keeps going. Not to the power of a half or anything like that. Okay. So we're saying that the first two are polynomials and the last one is not. Let's see, how do we do? So f can be written as this. Let me see. The first two functions are examples of polynomial functions because they can be written in the form of a polynomial where the powers are non-negative integers and the coefficients are real numbers. However, h cannot be written in this form and therefore is not a polynomial function. Okay. So the terminology of polynomial function, we often rearrange polynomials so that the powers are descending. So we usually put the term with the highest power first, and then the coefficient of that term with the highest power is called our leading coefficient. And the leading term is the term that has the highest power, right? So given a polynomial function, identify the degree, how to identify the degree and the leading coefficient, find the highest power of x to determine the degree of the function, identify the term containing its highest power to find the leading term, and identify the coefficient of the leading term. So I'm rushing a little bit. My battery is getting a little low. I'm hoping that we can make it, so I'm being optimistic. I got to find an adapter if I want to use this mic with the battery, so I'm just going to try to power through. Identify the degree, leading term, and leading coefficient of the following polynomials. Okay, so let's make a quick little table. So we have what? F of x, g of t, and h of p. And then we're asked to find the degree. I'm going to abbreviate leading term as LT, the leading term, and the leading coefficient I'm going to abbreviate as LC, leading coefficient. And I mean, I guess I could go something like this. Okay. That's decent. Okay. So for f, the degree is going to be the highest power on any term. So the degree of f is going to be 3. So then that means our leading term is this negative 4x to the third, and our leading coefficient is negative 4. For g, the highest power is the 5. So that means it's a degree 5. The leading term is 5t to the 5th power, and the leading coefficient is 5. For h, the highest power is the 3. So that means our leading term is this negative p to the third, and the leading coefficient is negative 1. I think we're good, all right? Describe the end behavior and determine the possible degree of the polynomial. Okay. So we notice that our graph goes up to the right and down to the left. So the degree should be odd. So a possible degree. So this could be a cubic function, right? Some odd degree with a positive leading coefficient. So we can tell that this graph has the shape of an odd degree power function that has not been reflected. So the degree of the polynomial creating this must be odd and the leading coefficient must be positive. Yeah. So given this function, express the function as a polynomial in general form and determine the leading term, the degree, and the end behavior. Okay, so I think we need to expand this guy. We're given f of x equals negative 3x squared times x minus 1 times x plus 4, right? So then this is going to be the same as negative 3x squared if we FOIL squared. 4 minus 1 is what, 3? And then if we distribute, negative 3x to the 4 minus 9x cubed plus 12x squared, right? So the degree, the highest power is a 4. So then our degree is 4. That means what our leading term is negative 3x to the 4. So, and our I'm just going to go ahead and put the leading coefficient. The leading coefficient is negative 3. So because our leading coefficient is negative, this graph should go down to the right. And because the degree of the polynomial is 4, which is odd, that means the other side does the exact same, so it should go down to the left as well. Okay. So we got these results along with this. So the degree is 4, which is even, and the leading coefficient is negative. So as x goes to positive infinity, y tends to negative infinity. As x goes to negative infinity, y tends to negative infinity. So what we said was correct. Oh, my battery. Okay. It is down there. I'm almost there. I'm like a little outside of 10 slides. So intercepts and turning points of a polynomial function. The turning point of a graph is a point at which the graph changes direction from increasing to decreasing or decreasing to increasing. The y-intercept is the point at which the function has the input value of 0. The x-intercepts are the point at which the output value is 0. So given a polynomial function, how to determine the intercepts? Determine the y-intercept by setting x as 0 and finding the corresponding output. To determine the x-intercept, solve for the input values that yield an output value of 0. Okay. So given this polynomial function written in factored form, determine the x and y intercepts. Okay. So often I prefer to start with the y-intercept. I feel like those oftentimes are easier. So if we're going to find the y-intercept, we set x equal to 0. Let me see. That's going to be a negative 2 times a negative 4, which is positive 8. Okay. And then for the x-intercept, we set y equal to 0 and solve. So since it's already factored, then we can quickly identify what values of x make this 0. So then it looks like it's going to be what? Negative 1, 2, and 4. So the y-intercept was 0, 8. I think that's what we got. The x-intercept, negative 1, 2, and 4. And you can see it displayed here. Okay, got 10 slides left. We're gonna try to make it. Given the polynomial function, determine the y and x intercepts. Okay, so again, I usually like to find the y-intercept first. I find that oftentimes it's easier to calculate over the x-intercept. Oh, you're getting squirrely. Okay, I'll let it be. Okay, so for the y-intercept, again, we set x equal to 0. So when x is 0, you can quickly find that it's going to be, the corresponding y is going to be negative 45. Now for the x-intercept, that's oftentimes it's a little bit more challenging. We need to set y to 0 and solve. So we have this x to the 4 minus 4x squared minus 45 equal to 0. All right. So I'm going to use a technique called u substitution, because I noticed that, like for instance, we're going to let u equal x squared, right? So then we can rewrite this. Let me see, it's going to be a u there, a u there. So if we let u equal x squared, the first term is going to turn into u squared minus 4u minus 45 equals 0. So then we want to see, well, can we factor this guy into some form like this where we have a u and a u? It's going to be plus and minus. Is it 9 and 5? So a negative 9 and a positive 5. Okay. But then now that, so from here we get that what? U equals negative 5 or u equals 9. But then we need to substitute back, or back substitute. So now we have x squared equals negative 5. I think there's no solution there, right? Because you can't find a real number that squares to give you a negative result. So that's an extraneous solution. And then we have x squared equals 9. We take the square root on both sides. So then x equals plus or minus 3. All right. So whenever we take an even root, we have to include plus or minus. Okay. So for the x-intercepts, we get negative 3 plus or minus 3. I know. I think we can make it. I believe in you. We're almost there. Okay. So these are the results I got for the x and y intercepts. So the y-intercept was 0, negative 5. And then, yeah, so they got the same thing that we got. You can see it here. So a polynomial of degree n will have at most n x-intercepts and n minus 1 turning points, right? Like if you think about a quadratic that's a degree 2, you have at most 2 x-intercepts and at most 1 turning point, so on and so on. Without graphing the function, determine the local behavior of the function by finding the maximum number of x-intercepts and turning points for this. Let me see. So we have at most 10 x-intercepts. And then at most 9 turning points. Now you're not guaranteed all of these, but you know that you're not going to have more than that. Yeah, I think that's it. There's a degree of 10, so there are at most 10 x-intercepts and at most 9 turning points. Okay, we're almost there. What can we conclude about the polynomial represented by the graph based on the intercepts and the turning points? Well, we have what? Now it looks like we could have 1, 2, 3, 4. We can say that the degree of the polynomial is at least 2, right? Because we could have more. So the degree is at least 2, and then we have what, 1, 2, 3 turning points. So that means it could be a degree 4 polynomial, right? I think it should be 4 because that middle part could be like up more, and we could have 4 x-intercepts, right? But we don't. But yeah, it looks like it could be at least a degree 4 polynomial. So So the graph has 2 x-intercepts suggesting a degree of 2 or greater, and 3 turning points suggesting a degree of 4 or greater. Based on this, it would be reasonable to conclude the degree is even and at least 4, right? Okay, we're almost there. Given this function, determine the local behavior. I guess they want the x-intercepts and number of turning points. So the x-intercepts, because it's already factored, we can find them quickly. Basically, the values of x that make these 0. Looks like we're going to have what? -3, 0, and 4. So if we were to expand this, we would have a degree 3 polynomial. So that means we have at most 2 turning points. Okay. Oh, and then the y-intercept is the origin. That's fine. So the x-intercepts are the origin, -3, 0, and 4, 0. The degree is 3, so the graph has at most 2 turning points. Do we have the graph? No, but that's okay. Okay. With 4% left, we made it to the end. I knew my baby could do it. All right, so we made it to the end. Okay, so it looks like we're building just to kind of explore like some techniques on graphing like polynomials and just different types of graph that we kind of encounter. Okay. So with that, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace.